Hey, Dr. Hedgren in class. My name is Douglas Stone.
I'm Spencer Jensen.
And I'm Kyle Duke.
We're really excited to present to you our project of adaptive volume control. So the genesis of this project kind of came from me, my love of music. I love to listen to music and audiobooks in the car, and it can be annoying, especially on road trips when you go through a variety of different roads and there's a lot of different road noise coming at you. You're constantly having to adjust the volume to get that sweet spot. And so what we wanted to do was to be able to create a sensor, a volume sensor that was able to isolate the volume of what you want to be listening to, be it your music or your audiobook or whatever, and recognize also the disturbance variable of like road noise or whatever, and take the sum total of that and make sure that you're always listening to your music or audiobook at the desired level over the road noise. And so we need something that recognizes the music and also the road noise and is able to adjust for those.
To do that, we used a PI controller that has a set point of about 10% above background noise. To isolate the tone that we're playing on our speaker, we used a fast Fourier transform. We defined our project with help from Doug right here, he's amazing. We built our hardware and coded it with help from Kyle right here, he's also awesome. And our hardware, here's our microphone, which is our primary sensor. We have our speaker, and we also have a transistor, which helps regulate the volume of our speaker.
And you can see here with this hardware, one of the first issues we ran into was difficulties in multi-threading. We were trying to have this one little CPU do several different tasks at once, and it just wasn't working. So we decided to build out this small little circuit with just transistor, a couple capacitors, and some resistors to kind of do one of those tasks in a more analog way and take that load off the CPU. And then our next challenge that we found was, in order to do a Fourier transform on this ESP32, we needed a custom distribution of MicroPython. That was a little difficult to find and install, but once that was done, it was pretty straightforward to just code the PID and get everything working.
Yes, indeed. That leads us to the meat of our presentation, the actual demo. So what we're going to do is we're going to show you the Thonny code up here, and it's currently running just based on our voices. People tell me I'm loud all the time. So we're almost maxing out. This is the percentage of our buzzer that's going. We'll wait for it to get quiet, and I'll add some just simulated road noise from my phone in the form of white noise. So we'll zoom in right here and start that, and then we'll pan out and show you how that's changing over there. So actually we need to wait for it to get quiet.
All right, building up around 45%.
All right, and then go ahead and zoom in there. And as I decrease the road noise,
You can hear the buzzer start to get just a little bit quieter.
if I take it away,
That serves as an effective disturbance test, I think.
mm-hmm.
From 45 up to 100 and back down again.
An interesting thing about the way we coded this was that we can imitate the buzzer's noise with a different device, trick the controller into thinking it's too loud so that it completely shuts itself off. So I'm going to do that on my phone right here. And you should be able to hear that the buzzer turns itself completely off.
And if you look up here, we can see that the volume controls at zeros.
There you have it.
Yeah, so there's our prototype. In reality, we'd be able to have more complicated code to isolate, say exactly what the frequency of the music or the audiobook that you're listening to is. There's our speaker coming back on again. But overall, this project was a really fun opportunity to kind of apply the things we've learned throughout this class and come up with something that we could really see us using in the real world.
So thank you for listening.